Hello everyone, welcome back to this channel. In this video series, we explore different concepts and aspects of writing VHDL code to model digital circuits. And this video specifically focuses on the different types of architectures used to model different types of digital circuits. Most specifically, in this video, we will cover 3 different architecture types: the data flow style architecture, the behavioral style architecture, and the structural architectural style. So without further ado, let's jump over to the video. As we've explored in our previous video, and as you may already know, the VHDL architecture describes how your VHDL system will behave. The architecture body contains 2 parts: the declaration section, right before the begin, and the body, or the begin to end section, where a collection of signal statements appear, and they are concurrent in their nature. We talked about concurrent statements in our previous videos and discovered the different types of concurrent statements and looked at 4 different types so far. Concurrent statements that contain the concurrent signal assignment, conditional signal assignments that uses the when, selected signal assignments with select, and processes. Processes are considered concurrent statements that will execute in parallel or concurrently with other sections of the code. However, it contains statements that are sequential in nature. We will not discuss processes in this video. However, we will do that in another tutorial. To fully understand process statements, which are concurrent statements that include sequential statements, we must first observe the different approaches to writing VHDL architectures. There are 3 main approaches to writing a VHDL architecture: the data flow style architecture, the behavioral style architecture, and the structural style architecture. In this video, to better introduce and understand each of these architectural styles, we'll need to observe how to design a certain circuit using that specific style. It's important to note, however, that in more complicated VHDL circuits, there is a general use of a mixture of these 3 styles. So let's start with the data flow architecture. In this architectural style, the circuit is represented by the flow of data through the circuit. In the data flow approach, circuits are described by showing the input and output relationships between various built-in components of the VHDL language, such as the use of AND or XOR components. The 3 concurrent statements that we have talked about in our previous video, the concurrent signal assignment, conditional signal assignment, and the selected signal assignment, are all statements that are found in the data flow architecture. Meaning, if your design only implements these statements, then you're using the data flow model. These signal assignments effectively describe how the data flows from the signal on the right-hand side of the assignment operator to the signal on the left-hand side of the operator. Look at the OR gate we've designed in our previous video through the use of concurrent statements. It's easy to understand that the signal on the right, the 3 inputs, will flow to the output of the OR gate on the left. This type of architecture can be intuitive and assists you in looking at the flow of data in the circuit by just examining the code. The data flow models will also allow you to realize how the actual logic will be synthesized. Now that we've understood the data flow architecture, let's take a look at the behavioral architecture. As you can imagine, data flow modeling works fine for small and relatively simple circuits. However, when circuits become more complicated, it's a better idea to use your circuits. When comparing the 2, the behavioral style architecture does not correlate to the physical connections in actual hardware. It does not reflect how the circuit is implemented when it is synthesized. However, as the name implies, the behavioral style architecture models how the circuit behaves or reacts to different inputs to the circuit, whereas the data flow would typically model the flow of signals within the circuit. The heart of the behavioral style architecture is the process statement. And this is the fourth type of concurrent statement that we've mentioned earlier in this video and also in our last video. As you will see in our future video, and briefly in this one, the process statement is very different from the other three concurrent statements. And the biggest difference is that within it lies sequential statements that are executed sequentially. The process will execute concurrently with other parts of the code, whereas the signals inside of this process is executed sequentially. Let's look at how we would model a D flip-flop using behavioral modeling. If you're not familiar with D flip-flops, they're considered as memory that registers an input, which is denoted here as D, on the rising edge of the clock and stores it until the next clock edge. If the reset signal or the RST signal is active, usually high, the output, which is denoted here as Q, is reset to 0. As we are dealing with an electrical component that's heavily dependent on the clock and synchronicity is important, it's the perfect use case for processes and behavioral modeling. Based on the clock and reset signal, we can model the behavior of the D flip-flop. So looking at the process, we can see that if the reset is equals to 1, we set the output Q to 0, whereas at the presence of a rising edge in the clock, then the Q is routed to the D, which is the input. We will talk about processes in more depth in our upcoming video. Finally, the final type of architecture is the structural modeling or structural architecture. And it is the way that defines the structure of a circuit through the combination of existing sets of VHDL models of certain circuits together to build a bigger circuit. In other words, structural modeling supports the interconnection of different circuit modules or models that are either modeled by the data flow or behavioral style, or even the structural architecture type as well, without having to describe the logic behind that circuit. Let's look at the half-adder circuit to further understand what structural modeling means. For us to model a half-adder circuit, we can build it by using an already existing module of an XOR gate and an already existing module of an AND gate. The XOR gate, which we can create using the data flow modeling, and the AND gate, which we can also create using the data flow modeling architecture, can be combined together to create the half-adder. So let's first examine how we would model the XOR gate. When we use the data flow architecture to model the XOR gate, we use the conditional concurrent statement when to set the output to 1 or 0 depending on the inputs. In the AND gate, we also use concurrent statements to model the AND gate within the data flow type of architecture. Finally, to build the half-adder circuit, we can instantiate each component within the architecture of the half-adder as follows, and route the inputs to the inputs of those submodules, and route the outputs of these components instantiations to the output of the half-adder. Okay, so now we understand what structural architecture is, but how can we instantiate those components within the structural architecture? Well, there are two methods, and we will discover them as you can see from the code. There are two ways in which we have instantiated the AND gate and the XOR gate. Let's start with the first method, which is the entity instantiation example. And this is the shortest type of instantiation, where to instantiate this entity of AND gate, we needed to name this component instantiation as something. And in our case, we named it AND gate. You could name it anything. You could name it gate and this is just an indicator for you that we have a component that is AND gate. And if we had multiple AND gates, it would be easier for us to differentiate the different AND gates by adding a number to the name. Then we would need to use the entity keyword, and we would need to specify the library where we would find the AND gate component. Then we would need to, right after the dot, mention the entity name, and in between parentheses, you can mention the architecture name. That's optional and it's considered good practice, but in our case, we haven't mentioned the architecture name of the AND gate here. Then we would need to map the ports, where we would need to route the ports of the half adder to the ports within the AND gate. So here we have routed input 1 or in1 to the input of the half adder A, and in2 to the input of the half adder B. Similarly, we have routed the output and out to the signal of the architecture and out S, which will then be routed to the sum. The second way you would instantiate a component is through the use of the component instantiation. And this has been implemented for the XOR. Right before the begin and within the architecture declaration, we have defined the component as follows. To do that, you would write the keyword component and then the name of that component just as in the entity. Then you would need to define the generics and port just as in the entity of that component. Don't forget to end the component. And then right after the begin, we do the component instantiation by naming that component instance and then mentioning the entity's name of that component, and then doing the mapping just as we did in our previous method, where we would do the generic mappings or the port mappings over here, where we would route in one of the XOR gate to the input A of the half adder and into of the XOR gate to B of the half adder, and XOR out, which is the output of the XOR, to the signal of this architecture of the half adder, XOR out S, which will then be routed to the sum output of the half adder. So that's how we could instantiate different components in different ways. The second method is a bit tedious when you have to change the entity of the component that you're instantiation, as you would need to do 3 changes. Changes in the component's original model code and 2 modifications within the structural architecture code. One right before they begin in the architecture declaration of the structural code, and one right after the begin of that component instantiation. So it would be much quicker and easier to use the entity instantiation. But of course, whatever is suitable for you, you can choose as your preferred method of coding. Thank you for watching this video. I hope you found this video useful. And if you'd like to support the channel, you can do so through subscribing or supporting the channel through Patreon, where you can find the notes behind this video in the Patreon page. And I hope to see you in the next video. Thank you so much.